Hello everyone and welcome back. My name is Mr. Kovalt and today I am going to be going over um, chemical formulas as conversion factors. Now, the reason that we can use this as a conversion factor is because we can use what is called the mole ratio. And the thing we got to keep in mind is first of all, these are the formulas for individual compounds. And so this can represent one molecule, right? So if I have one molecule of this substance, which is glucose, then that one molecule is going to have 6 carbons, 12 hydrogens, and 6 oxygens. Same thing with this substance here. This would be one molecule, which is 1 carbon, 2 chlorine atoms, and 1 fluorine atom. So we can view the formulas as either single molecules, or we can also view them in terms of moles. And so the ratio here, we can look at the ratio here of a whole to the part. With regard to individual molecules, particles. So if this was one molecule, then the ratio of one molecule to carbon atoms in the molecule is 1 to 6, because I have 6 atoms of carbon in one formula of the molecule, one molecule. Okay. Same thing with hydrogen. I have a ratio of 12 to 1. So if I'm taking the ratio of the whole to the part. So the whole is 1. So for every one of these, I get 12 hydrogens. For every one molecule of glucose, I get 12 hydrogen atoms. And the same thing goes with oxygen. For every one molecule of glucose, I get 6 atoms of oxygen. So there's a ratio between the whole and the part. I can also do ratios of part to part, right? So the ratio of carbon to hydrogen is 6 to 12 or 1 to 2, right? Or the ratio of carbon to oxygen in glucose is 6 to 6 or 1 to 1, okay? And I can do the same thing here. So why is that important? Well, as I said a moment ago, is not only does the ratio work with regard to individual molecules and the atoms that make up the molecules, but the ratio also works if we assume 1 mole of these things, right? Because if you remember, 1 mole is just a number. So 1 mole of anything is 6.022 times 10 to the 23rd of whatever that thing I'm talking about. And we talk about particles. So it's just that number. So this ratio between one of these and the number of atoms in the molecule doesn't change regardless of how many I have. So if I have 2 of these, so if I draw another one, C6H12O6, now I have 2 of these. So now the ratio, what's the ratio? So for every 2 of these, right, I have how many? I have 6 carbons and 6 carbons. So what's the ratio of these 2 molecules to the number of carbons? Well, it's now 2 to 12. And 2 to 12 is the same ratio as 1 to 6. So we're back to the 1 to 6 ratio. And that ratio holds regardless of how much I have. And this goes back to the law of definite proportions that we learned in another video on that. So if you don't remember the law of definite proportions, go there. So the ratio of part to whole stays the same. It doesn't change regardless of how many I have. So if I assume 1 mole of this stuff, then the ratio will work if I'm working in moles, right? So what that means is if I assume that I have 1 mole of this substance, then the ratio from whole to part also applies to the number of moles. So if I have 1 mole of this substance, then I have 6 moles of carbon. So the ratio of the mole ratio between whole and part is also 1 to 6. So 1 mole of this is equal to 6 moles of carbon. 1 mole of the glucose is equal to 12 moles of the hydrogen. And I can do that for any substance if I know the formula. So if I know this formula here, so 1 mole of this is going to be 1 mole of carbon. So it's a 1-to-1 ratio. 1 mole of this substance is to 2 moles of chlorine, because I have two atoms of chlorine per 1 molecule, and so on. And so now I can get a mole-to-mole ratio between the whole and one of the parts, or any of the parts. Or I can get a molar ratio between one part and the other. So now I can have an equality or a relationship between whole and part. So here, for example, if I have one of these, so then 1 mole of this whole substance, CCl2F2, is going to be equal to, and then I could choose, like maybe I'm interested in chlorine, so 2 moles of chlorine. So I have 2 moles of chlorine atoms in my molecule. So I get a ratio of 1 to 2 mole, a molar ratio of 1 to 2, right? So now I can use that equality as a conversion factor to convert between one part or the whole. So I can go from whole to part or part to whole. Same thing here. So if I have 1 mole of my glucose, C6H12O6, that would be equal to, say, 6 moles of oxygen. So 6 moles of oxygen atoms. So I get a mole ratio between the whole and the part. And now I can use this to convert from one thing to the other. So for example, if, let's say for example, they give me 2 moles. Okay, so I got, like, let's say they give me 3.5 moles of glucose. So C6H12O6. And they want me to convert, well, how many moles of oxygen do I have? If I have 3.5 moles of glucose, how many moles of oxygen atoms do I have, right? So I would put this over 1. And now I can go from, okay, so if I need to go from moles of the whole to moles of the part. So I have this equality here that I got from the formula. So I'm using the chemical formula as a conversion factor because the chemical formula gives me the ratio between whole and part, or between part and part, depending on what the problem is asking me. So in this case, I want to go from moles of the whole to moles of the part in oxygen. So now I can use this ratio of 1 to 6 to convert. So I have moles of the glucose on the top, so I want moles of glucose on the bottom. So I have 1 mole of glucose, C6H12O6, and I have 6 moles of oxygen atoms. So I'm going to put 6 moles of oxygen. Okay, so now the moles of glucose cancel out. I have moles of oxygen. So now all I have to do is multiply 3.5 by 6, and I get my number of oxygen atoms. So in this case, it'd be 18 plus 3, so 20. 21. So I get 21, and let's see. So this is exact. 1 to 6 is exact because it's a ratio between 2 whole numbers, and so I'm allowed 2 sig figs. So 21 is the number of moles. So 21 moles of oxygen atoms. And that's how you do it. So you can use the formula to convert from one thing to a different thing, right? And that's going to be really important in chemistry, because you're going to come up across a lot of problems where you're going to start with one thing and it's going to ask you for a different thing, and you're going to need to use the mole ratio in your formula or somewhere else. So keep in mind that you can use the formula to go from whole to part or part to whole. So if you run into a problem where they give you the formula and they give you moles of the whole and they want a part of it, or if they give you moles of the part and they want to know the moles of the whole, then you have to realize that you need to use the mole ratio from your chemical formula to do that. I will, in another video, I'll go over some good examples, a couple examples where this is going to work. So I hope this is helpful and clear, and if you like this video, go ahead and like it. Make sure you subscribe to the channel. Make a comment in the comment section. Tell me what you think, and if there's anything else you want me to cover, and hit the notification bell so that way you get notified for any other videos. Thanks for joining me, and I'll see you guys next time.